In this video, we are going to discuss questions on general organic chemistry and hydrocarbons. These are KVPY practice questions. So let us see. The first question: what number of unique molecules are obtained in the following reaction? So this is NBS. So NBS means it will perform substitution, free radical substitution. So that means NBS is a source of bromine radical. So N-bromosuccinamide, the structure like this. This on exposure to sunlight produces Br free radical. Now this Br free radical will interact with the substrate here. Substrate has allylic carbon at this particular position and this position. There are two allylic carbon. So when it interacts with Br for the first time, it will generate free radicals. So there are two possible free radicals getting generated. Let us draw both. One is like this, and the other one has to be like this. Now each of them can have a rearrangement because of the resonance. So this can be like this, and here it will be like this. So out of four free radicals, two of them will give identical product, that is these two. These two will give identical product. So on bromination, the reaction of another free radical will generate this product. So in case of this free radical also, you get identical product because the position, relative position is same. So this is one product which is possible. Then, as the question says, unique molecules. So we have to look at these two radicals. These two radicals will give two different molecules actually. So we can get Br double bond, and also so here Br dot, both will give two different type of molecules. So Br. In this way, there are three unique molecules here. So option B has to be the answer. Let us move on to next one. Yes. So the product C is, so there is a double bond here. So if you look at the double bond, Br to CCl4, that means it will be adding bromine. So basically after this, A will be PHC HBr CHBr. This will be A. Now once we get A, this is bromination. Bromination, that means anti-addition. So here we have 2 moles of NaNH2. That means this dibromo compound will become alkyne here. So PHC triple bond C PH will be the molecule B, because there is base here NaNH2 and it will perform elimination. So then we have Lindlar's catalyst. Lindlar's catalyst is PDBaSO4 and hydrogen. So this Lindlar's catalyst will basically reduce this alkyne to alkene, and that will give cis-alkene. Cis-alkene is obtained. So as a consequence, after Lindlar's catalyst, the product obtained will be PHC, H, double bond C, H, PH. So if you look at the options here, it is option A that can be correct answer. So that is correct answer. Let us move on to the next one. Third question. Select incorrect statement from the following. So yes, there are four statements. The first one, they differ only in the arrangement of electrons in different resonating forms. Okay, so basically this statement is about resonance structures. So the resonating forms differ only in the arrangement of electrons in different resonating forms. So this is a correct statement. Resonance hybrid is more stable and has maximum contribution of least stable canonical form. Actually, resonance hybrid is more stable, that's true, and has maximum contribution of most stable canonical form, it should have been. So this is a wrong statement. So option B should be the answer. Let us go through the other two options. Difference in the energy of resonance hybrid and most stable contributing structure is called resonance energy. This is a true definition. The difference in the experimental and calculated enthalpies of formation is called resonance energy. This is also another definition, but we use more of this definition, the one given in option C. So here our answer, as it was required to mark incorrect statement, is option B. So option B is the correct answer here. Next question. A hydrocarbon A has no chiral carbon and gives white precipitate with ammonical silver nitrate. Okay, here the point to note is no chiral carbon and white precipitate with silver nitrate, ammonical silver nitrate. That means it should contain either aldehyde or alkyne. Let us see the du. What is du of this? Degree of unsaturation is 10 into 2 plus 2 minus 12 divided by 2. That's equal to 5. So du 5. So degree of unsaturation is obtained as 5. That means there can be two triple bonds, because each triple bond contributes for du of 2. So there can be two triple bonds. We will see. Because this alone cannot give all the information. Let us read the question ahead. A on reacting with H2PT gives B. So it is after reduction, it gives B. du for B, let us see, is equal to 22 minus 20 by 2 is equal to 1. So after hydrogenation also we have 1 du. That means it's a aliphatic ring. B has a aliphatic ring. Aliphatic, it's a alicyclic compound. It's a cyclic compound. So I should write, instead of aliphatic, let us keep it as alicyclic ring. It's alicyclic ring. So that's about B. Then A also gives C on reacting with acidified KMnO4, and C has 4 oxygens. C has 4 oxygen. That means, and it's acidified KMnO4. So du of C, if we find out, it is like 16 minus 12 divided by 2 is 18 minus 12 by 2. It's 3. That means with the 4 oxygen, that means it has 2 carbonyl groups. That means this is a carboxylic acid, surely. Let us see ahead. On treating with acidified KMnO4, which on treating with soda lime gives D. If we monochlorinate D, it gives only one isomer, the compound D is. So because it should give only one isomer on monochlorination, it's very clear that it cannot be A, it cannot be C, because it has more than one type of carbon. So monochlorination will give more than one type of isomer. But B and D have only one type of carbon. That means it will give only one isomer on monochlorination. So let us check now. Total 10 carbon should be there here, and here it's 8. So in case if it is obviously it is a decarboxylation here, so 2 carbon will be lost. So D must have 6 carbon. So in that way we arrive at answer B. So this much analysis is needed. We can also write the product as it is, like if it has to be 6-member ring, then 2 other carbon, total 10 carbon is there, so it should have a triple bond like this, and it should be 1,4 substitution only, otherwise it will form a chiral molecule. It can form a chiral molecule. So it's not chiral because now it has a plane of symmetry. I mean, it's not a chiral carbon now. These carbons are not chiral because of identical environment. So if this group is at any other carbon, it will not have identical environment and it becomes molecule with chiral carbon. So it has to be at 1 and 4 direction only. So this on treatment with AgNO3 and NH3, ammonical silver nitrate, it will form Ag, and here it is CAG. So this is going to be precipitate. So this compound on reacting with H2 and PT will form this compound. So here we have ethyl cyclohexane. So this this is B actually. Okay. And they have mentioned A reacts with acidified KMnO4 to give C. So let us react A. So yes, in presence of acidified KMnO4, it should give carboxylic acid 1,4 position. Then this on soda lime, that is decarboxylation, should give cyclohexane. So this is our D. So in this way we can analyze the question. So option B should be our answer. Let us move on to next question. Correct order of acidic strength is. So this is a derivatives of benzoic acid. So here the most acidic molecule is this one. Why this one? It's very interesting to find that after dissociation, this forms actually this anion. This is the anion formed, minus H plus. And this anion is extremely stable due to hydrogen bonding. There is a hydrogen bonding involved here. So if you look at the bonding, this is one hydrogen bonding and there is another hydrogen bonding at this side also. So this is a hydrogen bonding. Because of this, the anion formed is extremely stable. That's why this becomes most acidic. So first one is most acidic. Then it is 2. Why 2? Because here OH is at meta position to COOH group. So this OH will not offer plus R effect here. Only minus I is operative. So as a consequence, it will surely enhance the acidic strength of this carboxylic acid. So it is 2. Then the first one is most acidic. Then it is second one. After that, it cannot be third one because here plus R effect is operative for OH. So as a consequence, it will be fourth one, then third one. So now if you look at the options here, the options, it's going to be 1, 2, 4, 3. So it's option B. That is our answer. Let us move on to next question. Decreasing order of basic strength of A, B, C and D. So this is the molecule given here. So we should know basic strength is proportional to electron density on nitrogen. This is the main point we need to check here. So if we look at that, there is one nitrogen here, it's primary. So A is primary, C is tertiary nitrogen, amine. B is aromatic amine. Even D is aromatic, but there is NO2 here and there is only CN here. So if we decide among A and C, then it's almost solved actually. So we know for amines, basic strength is secondary, then tertiary, then primary. This is for aliphatic amines. The secondary should be most basic, then it should be tertiary, then primary. So in that way, C will be most basic here, then A. And after that, it will be B because Cn is only, yes, Cn is offering minus R as well as minus I, but in both minus R effect as well as minus I effect, Cn is less effective than NO2. NO2 is a nitro group which is very more powerful in fact than Cn. So as a consequence, NH2 at D will be more, the basic strength, the electron density on this nitrogen is decreased. So it will be B here and D. So this order we can find it in option D. That should be the answer. Let us move on to next question. When following compound is heated in presence of concentrated sulphuric acid, an aromatic compound B is obtained. Okay, yes, this compound if we dehydrate, it will become naphthalene. Total number of resonance structures for the carbocation intermediate formed in the reaction and number of pi bonds in B respectively are. So the point is we should know what is B here. So B is naphthalene. So it will be something like this. So this has how many pi electrons? pi bonds 5. So there are 5 pi bonds here. So option D is ruled out. Let us write the resonance structure for the carbocation form. Very essential, because otherwise we will not be able to get the answer here. So this bond can easily shift from here to here. So I will mark it in yes. Then the positive charge will come on the adjacent carbon. The plus charge will come here and double bond here. Now we can shift this bond here. So it will be positive charge here, and we get this particular arrangement. Okay. Now next this bond will shift here, and we get double bond here, plus charge here, and we get something like this. So next again this has to move, and we get positive charge will come here, but this positive charge has a completely different position of double bonds than this structure. So there is one more possibility of having another carbocation. So here this bond, if it moves, it will become a double bond over here, and we have this carbocation. So this one, the first one and the last one appear to be same, but they are different because of the position of double bond in this particular ring is different. So in this way, 1, 2, 3, 4, 5, 6 and 7. The total 7 resonance structures are available. So 7 and 5, option B should be the answer. So 7 resonance structures for the intermediate carbocation. Let us move on to next question. Carefully observe the graph given below and select correct options about the graph. So this graph is energy versus reaction progress. So it's based on the reaction mechanisms. Chlorination of methane. Chlorination of methane follows free radical mechanism. So this is not the graph for free radical mechanism. TS1 and TS2, that means there should be some intermediate getting formed, preferably carbocation here. Though it is not mentioned, it is imperative that it should be carbocation. Sulfonation of benzene. Okay, this is the graph for this process, sulfonation of benzene. We have benzene here. Sulfonation means we have SO3 as a electrophile, and this bond will basically migrate onto this. So it forms something called as uranium ion. So this uranium ion is a carbocation. So because of this, it has the name. So now next mechanism is very simple. This hydrogen will get exchanged and we get SO3H here. So in this way, this is a benzene sulfonic acid. Sulfonation of benzene involves uranium ion, which is a carbocation. So this graph represents the mechanism of sulfonation of benzene. Aldol condensation involves carbanion, and this is not the graph for that. And aromatization of ethine, I consider that to be a polymerization type of reaction, and we generally don't study their graphs. That's about the question. Next, product obtained in the following reaction is reaction A is reduced in presence of FeHCl to get B. Okay. IUPAC name of B is FeHCl converts NO2 group to NH2 group. Okay. First we need to find this A and then get B. Then only find out the IUPAC name. So first alkyne is ethine, red hot iron tube at 73 Kelvin. So it will actually convert CH triple bond CH Fe at 73 Kelvin. Will convert it to benzene. And then it is going to be Br2 FeBr3 will be bromobenzene. This can be treated with CH3Cl and AlCl. There is a Friedel-Crafts reaction, alkylation. So it will form 4 bromotoluene. This will be the major product. So we consider only major product here. This one on treatment with nitric acid HNO3 and H2SO4 is nitration. So now we have two options. Now. Br here. Br is a para-directing, ortho-para-directing. So CH3 came there. Now out of these two, which one will dominate and what product should come is our challenge. Now the point is, so because bromo group is going to show plus R and it's going to be ortho-para-directing, so that will dominate. So as a consequence, NO2 will come at para position to bromo group. So this one is our A. And once we get A, what we need to do is reduce it to B. So FeHCl. This will convert A to this compound Br NH2 CH3. So this is the product obtained. This is B. So now let us name this. This is aniline actually, because NH2 group attached to benzene ring. So numbering wise, it should be 2, 3, 4, 5, because lowest set of locant, and among the substituents, bromo should get the lowest possible number. So it's going to be 2 bromo 5 methyl aniline. So it's option 2. Second option is our answer. So that's about compound. The question number 9. The last question for this set. Correct product for the following conversion is, yes, we have oleum here. So that means it is going to do sulfonation. It's sulfonation. So if it is sulfonation, then SO3H is introduced. So here there are two groups here. One is plus R group and this is ester. So this is ester here. Because it is ester, this carbon is going to, this ester group is going to offer minus R to this ring, and this oxygen is going to offer plus R to this ring. But this plus R is much weaker compared to plus R of this OH. So as a consequence, electrophilic substitution of SO3 here, it's an electrophilic substitution only, which is going to be like based on the directing influence of these groups. Because OH group is very powerful in terms of plus R, it will actually direct incoming electrophile to either para position or ortho position. Of course, both it will direct. The major one will be the one with substitution at para. So our product here will be something like this. OH, COO. This is our reactant, SO3. Oleum gives SO3 as an electrophile. So this will undergo substitution in this ring, SO3H, it will form, and it will be OH here, C double bond OO. This is our another ring. So this is going to be the product. If you look at the options here, it has to be option SO3H. It cannot be here. This is not possible. This is also not possible. This is correct position. So option C should be the answer. So that's it for this video. So keep practicing and meet you in next video. Thank you.